Okay, so a power function is any function in the form f of x equals a times x to the n. So this a here is the coefficient. So you already know what that word means, and then n is the exponent. So a and n have to be non-zero, constant real numbers. Can someone tell me why can we not have n equal 0? Because then the base would always be 1. Right, that's dumb. That's just, it's just a straight line. We need it to be a power function. And why can't a equal 0? Because then the whole thing equals 0. Because if the coefficient 0, anything times 0 is 0. Okay. So here's 4 different types of monomial functions. So if a bicycle, bi means 2, what does mon mean? 1. Like a monocle, 1. So a monomial function literally has one term. This is why if you have something like x to the 6th power, it roughly looks like x squared. Because it's not x to the 6th plus 5x to the 5th and blah, 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 x to the 4th. It's not all these terms. It's literally one term, one monomial. So it roughly looks like an x squared term. This is why we play the game of function dance. What does it look like? Do we understand what it should be? So if you have an even exponent and a positive coefficient, so you have an even exponent and you have a positive coefficient, this is what it's going to look like. Can someone give me an example? Robert, what would be an example that fits here? Something with an even exponent and a positive coefficient. Robert. Yeah, give me an example. So give me a positive number. Any number. 6, okay, and give me an even number. 4. 6x to the 4th. Perfect. Look at you go. Shane, you gonna give me another example? Something that has a positive coefficient, even exponent. Perfect, exactly. All of these are roughly going to look like just a parabola. Granted, some of them are going to be skinnier than others, but they all are just a U shape. Notice that the domain, it's a polynomial. It's just all real numbers. The range are the y values. There are no y values less than 0, which is why it goes 0 to infinity, because it's all the y values above 0. It's continuous for all real numbers, right? Where does it touch the x-axis and y-axis? 0, 0, right? That's where the intercepts are. We have end behavior. I mean, you can read through all of this. We went over it last semester. And we're also going to go in depth to every single thing. So I'm going to move on. So that's one example. So even exponent, positive coefficient. Notice the end behavior, they're going the same way. What if I have negative x squared? So a negative coefficient, but an even exponent. So let's see. Do you want to give me an example, Isa?
Yes. Negative 5x.
Perfect. Negative coefficient, even exponent. Ellie, another example?
Negative 3.
Good. Last example? Yeah.
Negative 7x.
Awesome. So you guys got it, right? Even exponents, they go the same way. Positive in front goes up, negative in front goes down. Cool. So by having your intuition, you know what the graph should look like, it makes it faster to double check your work. Okay, so what if we don't have an even exponent? What does x cubed look like? Now let's try one more time. X cubed. Negative x cubed. X cubed. Negative x cubed. Hey. See, we should be on the Instagram. No. Okay, whatever. Whatever. They always want math on there. Then they came around the open house and they wanted to take pictures of the paper. I was like, nope. So I got a bunch of people and they were playing with the calculators. Not that that's better, but it's better. Okay, so what if I have a positive coefficient, but we have an odd exponent? So Let's just keep going down. Bradley, do you want to give me an example where it has an odd exponent but a positive coefficient?
2x.
Exactly. Positive coefficient, odd exponent. Next. Just x cubed? That's so boring. 7x to the 7. Okay, whatever. Next one, Mika, do you want to give me an example?
6x to the 5th.
Exactly. Notice all these are monomials. They all have one term. So if I wanted to graph 7x to the 7, it's going to roughly look like x cubed. If I want to graph 6x to the 5th, it's literally going to look super similar to x cubed. It just might be a little like skinnier, whatever. Same shape. I don't know. You can read over this. We're going to be going over examples to talk about it anyway. And then lastly, if I have an odd exponent and a negative coefficient. So the way I remember how to draw x cubed, because for me, I'm graphing it, so like you are looking at me and I have it graphed correctly, but like if I was looking at myself, I'm like, this is totally backwards. So the way I remember it, so if you have x cubed, if I have x cubed, if I take a positive number times itself 3 times, it's going to be positive. But if I take a negative number times a negative, it will be negative. So a negative multiplied by an odd number of times is still negative. And then once I remember x cubed, I can just flip it if it's reflected. And if I know x cubed, I know x to the 5th, x to the 7th, etc., etc. All right, so let's finish out. Hannah, do you want to give me an example of where I have a negative coefficient, odd exponent?
Negative 2x to the 3rd.
So a negative coefficient, odd exponent, perfect. Next.
Negative 5x.
Perfect. Next. Awesome. Yeah, all of these are right. And you guys give me the examples. That's perfect. All right. So it's really the main thing. And then, tomorrow we're going to start class with a little dance party. Yeah. Okay. Don't be lame. It's 2020. We gotta bump it up. Whatever. Okay, so example 1. This is a lot of work. So there's a lot of stuff to do. We have to graph and analyze each function, right? So we have to talk about the domain, the range, the intercepts, end behavior, continuity, where it's increasing or decreasing, aka huge review of chapter 1. So do we know what this is going to look like? On the count of 3, we're going to use our hands. 1, 2, 3. Okay, so x to the 6th power, it has a positive in front of it, even exponent, and roughly looks like a U shape. So you know it's going to look like a U. So really for these graphing, because there's going to be one on your quiz, which is no calculator, you only really need to have a couple points. Maybe 3 or so. It just depends on the graph. What? Right. Yep. So what would be the best number to plug in first? 0. What is 0 to the 6th power?
0.
0. Okay. 0 times anything, 0. Perfect. Another easy number to plug in is we always choose 1. All right. So f of 1 is equal to 1/2 times 1 to the 6th power. So that's just 1/2 times 1, which is just 1/2. And then since it's symmetric across the y-axis, it's even symmetry. It's an even function. Or you could say, hey, what's f of -1? That's just going to be 1/2 times -1 to the 6th power. Oh, a negative times itself an even number of times is positive. So it also is 1/2. So this is going to be a U shape. We know that. We also know it's going to be very, very skinny, because it's the 6th power, not the 2nd power. So if I want to draw it, it looks something like this. And notice I'm not touching the x equals 2 lines, because 2 to the 6th power is 64. Half of 64 is 32. That's off our graph. But I wouldn't be super, super picky. If you drew something like this, I'll be like, well, I mean, you get it, but it's kind of wide. But as long as you drew your U shape pretty skinny, I would be fine with it. The main thing I'm looking for is, do you have the point 0, 0? That, non-negotiable. You have to have 0, 0. You have to touch the axis there. And it should be pretty skinny. X to the 6 is pretty skinny. Is it facing the right way? That's what I care about as far as graphing, because you won't have your calculator, so I have to be reasonable. So just keep that in mind. I think we left off on Daniel. What's the domain for this?
Negative infinity to positive infinity.
Perfect, because domain we always talk about in terms of x. There's no x value that I plug in that would not give me a y value. Andrew, what's the range? Sorry, I'm going around this way. 0 to infinity. Include 0 or not? Include 0 or not?
Yes.
Goose.
No. What?
Include 0 or not? Okay. Square bracket 0 to infinity. Because I'm touching the axis. Yes.
Can you explain how you got the name?
So the domain are the x values. There's no holes, there's no jumps, no vertical asymptotes. Since it's a polynomial, we know it's all real numbers. Even though it's a very small polynomial, only one term, technically it's a monomial, it's all real numbers. All right, Jake, the x-intercepts. 0, 0. Yep, so intercepts I want as an x comma y pair, because if you just say 0, x equals 0, that's a line. I want an intercept, a point. A point is an xy comp. Do you have a question? Robert, do you have a question? Okay. Y-intercept. Ethan.
0 times 0.
Yep. So the x-intercept is where you touch the x-axis. Y-intercept is where you touch the y-axis. They're at the same place. This is because I didn't shift it. I didn't have a horizontal translation or a vertical. So if I had 1/2 x to the 6 plus 2, everything would move up by 2. And if I would have 1/2 x minus 2 to the 6, everything would shift left and right to the 6. But I don't have a translation at all, so that's why my intercepts are the same. What about end behavior? Next. As x goes to negative infinity, what's happening to the y value? Goes to positive. So the hard part here is as we go to the left, y is going up, which is positive. So I say positive infinity comma does not exist, because technically it's not a number. Infinity is not a number. Sorry, is that a little easier to see? Blow it up a little bit. And then as we go to the right, Rocky, as x goes to the right, what's happening to y?
Infinity does not exist.
Yeah, it also goes to positive infinity. And we tack on does not exist. So one thing to note, when we're talking about continuity, increasing, decreasing intervals, these are all in terms of x. Just to be clear, just to help you remember, these next three are only in terms of x. So we're talking about the domain, where it's continuous. So Sarah, where are we continuous for my function?
We're continuous everywhere.
Everywhere. So how do I write that?
All real numbers.
All real numbers in negative infinity to infinity. Yeah. Then I'm back to the start. Robert, where am I increasing?
You are increasing number of percent. 0,
0 to infinity. 0 to infinity. So from here all the way over, as I increase my x's, my y's keep getting bigger and bigger. And we don't include 0 because 0 is a critical point. It's our turning point. It's like the middle negotiator. It's a neutral party, right? It's not increasing, it's not decreasing. It's the point where you're changing. So you don't include it. Do you have a question?
Yes.
Cool. Shane.
Wait, why is it
Yep.
okay forever?
It's continuous everywhere because there's no holes. Because it's a smooth decreasing. Perfect. So from negative infinity all the way to 0, my function's getting smaller. And then at 0, it switches, and then from 0 to infinity, it increases. So these intervals are always in terms of x. Which x values, where the x values were increasing, where the x values were decreasing. Okay, so I want you to look at the next one. Look at B. think about what this would look like without plugging into your calculator. Do you roughly know what it's going to look like? Use our hands in 3, 2, 1. Do we know? Okay, so it will be something like that, right? Yeah, because the negative flips it. X to the 5th is a negative, x to the 5th, 5 is an odd exponent, so normally it would look like this, but the negative flips it, so it's going to be going up on the left, down on the right. So you can go ahead and draw that in. So we knew 0 to the 5th power is 0. 1 to the 5th power, 1. Oh, the negative in front, that's how I know it goes down to -1 right here. So I'll write that out for you. So I have -1, 1, and 1, -1. There's my graph. Roughly looks like x to the 3rd power flipped. So notice we have a negative coefficient and an odd exponent. I'll give you about 15-20 seconds. See how much of the left side you can fill out, and then we're going to go over it together. So I want you to try filling out this left side. Give it a shot, see how much you can figure out yourself. Discuss with the person next to you if you need to.
I know that it's for this one, I'm just not sure to what exactly.
Yes, that's probably the hardest question on the page. I have to think who I'm going to give it to. Perfect, okay. So, thing I left off on you?
Yeah.
Yes. What is the domain of this function?
All real numbers.
Wonderful. Ellie?
The range is -1.
Cool, exactly. So the range, all numbers, domain, all real numbers. This goes on forever in all directions. Yes, next.
So 0, 0.
Yeah, because that's where it touches the x-axis. Bradley, where does it touch the y-axis?
0, 0.
Exactly. Let's see. Andrew Benson. End behavior as we go to the left side. What's happening to my y value?
It's infinite.
It goes to infinity, positive infinity. Right? And we also say, well, technically it doesn't exist. When we hit chapter 12, like, we're going to hit all the limits. It's exciting. If we have enough time at the end of chapter 12, I might teach you some derivatives so you're more prepared for next year. Right side limit, Mika.
-infinity.
Exactly. As x goes to the right, y is going down to -infinity. Perfect. Do we have questions so far? No. All right. Hannah, where is it continuous?
-infinity.
Exactly. -infinity to positive infinity. It's continuous everywhere. So, helpful hint. Most times your domain is going to be very similar to where you're continuous. The only things you have to look out for are jump discontinuities, because you could have a graph where it has a hole right there, but the domain keeps going because x is defined there, but technically it's not continuous. So the only difference between your continuous on interval and your domain is like jump discontinuities. That's really the only place where you can have it and not be continuous. If you have a hole, it won't be in your domain or won't be continuous in there. If you have an infinite discontinuity, it won't be on your domain or your continuous interval. And then where am I increasing, Maya? So this is mean. This is a hard question. So what's happening to my graph? It's always decreasing, right? Because you always read, I did not remind you guys of this, when you're talking about decreasing and increasing, you're always going from left to right. So if I'm going from left to right, I see that I'm always decreasing. So that was mean because it's not increasing ever. Not applicable. Cool. 2 pages done. Yeah. Cool. Okay. All right. Do you have questions on this so far? I'll make sure I'm not rushing you guys. I think this chapter went pretty well last year. And mid-semester, that's where it might get a little more difficult. Okay, so C, example C. We have f of x equals 2 times x to the negative 2 power. So I'd like to rewrite this. This is the same thing as saying 2 times 1 over x squared. So it's 2 over x squared. So right away, you might be like, I have no idea. How do you even graph this? What the heck? But do not fear. Have a little review to do. So recall what 1 over x looks like. Do we know what it looks like? 1 over x. So one thing we do know is it's a rational function, right? It's a ratio, and we know whenever I have a fraction, I can't have the bottom equal to 0. So when x equals 0, I'll have a vertical asymptote. What else do we know? So in English, you have a hyperbole, but this is a hyperbola. Yeah, with the like little arcs. No, it's fine. Looks like this. So that's really all you have to know, and then you can just reason through the rest of it. So if we know what 1 over x looks like, let's think about what 1 over x squared will look like. So 1 over x squared, all I have to do is take the blue one, right, the 1 over x, and square it. So it makes it pretty easy when I have a positive number. Right? Positive times positive is positive. Positive times positive is positive. So this thing, it still stays a curve somewhat. It's going to be a curve, whatever. But what happens to the negative? A negative times a negative? Times positive, negative times negative. Oh, so this thing just flips over. So it turns into like a symphony guy, right? A conductor. You guys ever watch those? No? It's like this? No? I grew up playing trumpet, so I was like used to the conductor going like this. What's that face? Are you judging me?
No.
Okay. I also learned how to play saxophone and clarinet. Okay, so that's what 1 over x squared looks like. What about 1 over x cubed? That'd be like the first. 1 over x to the fourth. That's like the other one, right? It just keeps flipping. Because when you have 1 over x, and you put a negative x in, well, if you're multiplying a negative by negative, it just flips it on top. So you're constantly just flipping the second arc from top to bottom. Okay, so we roughly know what this is going to look like. Cool. We can plug in some numbers, right? If I plug in f of 1, I have 2 over 1 squared, which is just 2. So 1 comma 2. If I plug in f of 2, I have 2 over 2 squared, which is 2/4, 1/2. And then notice on my, I don't know, what's the math term? Swoop-de-doop. The swoop-de-doopties, they don't touch the axes. They don't touch the axes. Secretly, there's a horizontal and a vertical asymptote. We haven't really covered that yet. We knew there's a vertical asymptote, so we won't touch the y-axis. Later in this chapter, I believe we're going to be talking about horizontal asymptotes, so you may not know it yet. Bigger on bottom means horizontal asymptote at x equals 0. So we're not going to be touching the x or y axes. So I'm going to connect these two dots in an arc-like fashion and go along them. And then I know it's symmetric, so the right side is just going to be reflected across the left. So instead of having 1 comma 2, I'll have negative 1 comma 2. And instead of having 2 comma half, I'll have negative 2 comma half. Are they outside again? At least they're not having a horror. All right. They did that. Yeah. One time I look outside, and it's someone in a chair lifting him up. Nope. I'm not even joking. I was so mad. Okay. Fun fact. Let's go back to some intuition. So the difference between 1 over x squared, 1 over x to the 4th, 1 over x to the 6th, all of these numbers, what happens, and I don't know if you really need to know this, but you see this part right here, it just gets closer and closer and closer to the axes. So that's it. As you get higher exponents in the bottom, it just sucks it in closer to the axes. Whatever. Did you really need to have points here? If I give you a problem like this, all I care about is you not touching the axes and having them in the right quadrants. Like the blue, that would have been fine. Is it a little sloppy? Yes, but I mean, it's fine. Because the things I care about, did you touch the axes? No, you should not touch the axes. Is it in the proper quadrants? Yes. Okay, cool. That's all I really care about for this one. Okay, so we graphed it. Now we can talk about the domain, range, blah, blah, blah. I left off on tall. What is the domain here?
I'm not sure.
It's all cool. So domain are the x, range is the y. So I'm looking at the x values. Is there an x value that's not defined? Yeah. So literally that's the one I want to cut out. So if I just want to cut it out, it'd be negative infinity, comma 0, union 0 to infinity. All I'm doing is I'm just cutting that one piece out. Daniel, next. What is the range?
1/2 to infinity.
So you got the second part right, to infinity. So it looks like it's getting closer and closer, but never approaching y equals 0. Yeah. So I don't want to include y equals 0 because that's where I have an asymptote. I have a horizontal asymptote. I don't want to include it, but I want to go right up to it. All right, and then this leads me to Andrew G. What is the x and y intercepts?
None.
None. It doesn't touch. Doesn't touch the x-axis. Doesn't touch the y-axis. All right, Jake, what's my end behavior?
As x approaches infinity, the limit is also, I think it's 0.
Yeah, because as we go to negative infinity, my y value is getting closer and closer to a value of 0. And as we go to positive infinity, it also goes to 0. Exactly. What? No, it doesn't. Okay. Ethan, help us out with continuity.
Is it the same as domain?
Is it?
Or like this answer,
Yeah.
doesn't include 0.
Right. Where is it continuous? Everywhere except x equals 0. So it's continuous from negative infinity to 0, union 0 to infinity. All right. Danny. Where is it increasing? To 0? Yeah. Because from the left side, negative infinity all the way to 0, it's increasing. And then Rocky, where is it decreasing?
0 to infinity.
0 to infinity. It's going down. Should have spread them out more. Okay, do we have questions about this so far? Yeah, 10 more minutes. Let's keep going. Okay, so those are power functions. Now we're going to talk about radical functions. So a radical function literally has a fraction. So exponential form, you have x to the p over n. And as one of my precalculus students famously said last year, top dog in the house. That will help you. And I'll explain what the heck that means. So this p is just standing for the power, and this n is your index. So I'm labeling them so I can go over to the radical form. So this n is your index. Which root do you want? Your index is the root you want. So an index of 2 would be a square root. Index of 3 is a cube root. And then p, once again, this is your power. And x we give a fancy name, radicand. So what I mean by top dog in the house is if I have something like x to the 5/4. So the top dog, aka the one on top, stays in the radical. So to write this, I would have, let's see, the bottom comes out, 4th root of x to the 5th. Top dog is in the house of the radical. No, okay. It may be life-changing, it may not be, it's fine, but it just, if it helps you, it helps you. Okay, so this is an expression, a radical function, literally f of x equals some radical. So we learned how to graph even and odd exponents, but now we're going to deal with fractions. One thing, I think this is good to do now. Okay, so if I have a graph, what does y equals x look like? It's just a straight line. This is y equals x. And keep in mind, y equals x, that's just to the first power. Do you know what y equals x to the 1/2 looks like? Yeah, square root, right? Because 1/2 is literally the same thing as square root. Y to the 1/2, okay. So this is x to the 1/2 power. And what about powers that are greater than 1? X to an exponent that's greater than 1, what will it look like? Right, x squared. It curves upwards. So the reason I'm showing you this is try to help you build intuition. So if I have an exponent less than 1, it's going to be curving down. If I have an exponent greater than 1, it's going to be curving up. So for example, x to the 3/2, x to the 5/4. When you have a fraction where you simplify it and it's greater than 1, it's going to be curving up. It's kind of weird. I mean, because you're like, wait, the square root of x cubed doesn't look like a square root. No, it actually is curving up. Whenever your fraction, right, the exponent, that's a fraction. If that's greater than 1, it's going to be curving up. Okay, just trying to save you some heartbreak later. Let's keep going. This should help you. Yeah. I think there's a similar picture of what I put as your MyJag tile. Okay, so we're going to come up with a couple examples. This is if you have an even index. So examples of this is like square root of x cubed. That's just x to the 3/2. If I have something like 4th root of x squared, what would this be equal to, Sarah?
X to the 1/2.
X to the 1/2, right? Because it's x to the 2/4, which is just x to the 1/2. I could have maybe 6th root of x, that's just x to the 1/6 power. Cool. One thing to note, and this is what we talked about when we went over domains in chapter 1, if you have an even root, it's only defined on the right side. Notice there's only one end behavior. Only one side of end behavior. And your extrema is always at your endpoint. So, pretty special. If you have an odd root, you can put a negative under it, right? So we talked about this. The domain of x squared, the domain of square root of x, fourth root of x, 6th root of x was 0 to infinity. But if I had a cube root or an odd root, it was all real numbers for our domain. Remember that, chapter 1? Throw back a couple months. So you can have a negative under, because a negative times itself an odd number of times is negative. That's acceptable. All right, cube root of x is just x to the 1/3. 5th root of x squared is just x to the 2/5. I could have 7th root of x to the 8th. That's just 8x to the 7/8, 8/7. And they have both end behaviors. Yeah. Okay, time to try the next example. think that would be a good stopping point after this example. Yeah. So, graph and analyze each function. Describe the domain, range, intercepts, end behavior, continuity, and where the function's increasing or decreasing. So to help me understand what this is going to look like, there's a couple questions. Is it just going to be swoop arm at a movie theater, or is it going to be both sides? Is it going to be swooping down, or is it going to be moving up, right? It depends on the fraction of your exponent. Oh yeah, the movie theater thing, like square root. Ethan, put your arm on Jake. That's the shape of a square root. That's what I showed them. Maybe I shouldn't have told you that. No. Okay. Whatever. I don't know. I'm just trying to help people understand graphs. That's all I want. That's not what I want. I just want you to critically think. Okay, let's rewrite this and see what it should look like. So I'm going to write this as 5 times 2x cubed. You don't have to, but you need to know what it's gonna, like, what my goal is to write it so I see the exponent and decide if it's greater than or less than 1 to tell me if it's swooping down or if it's coming up. Yeah. Also, I need to know, is it an even or a like odd root? Am I going to have like both sides or just the one side? All right, it's the same thing as 5 times square root of 2 times x to the 3/2. So this 3/2 tells us what we need to know. So it's an even index, so it's only going to be half your graph, but 3 over 2 is greater than 1, so it's going to look similar to a parabola in the sense that it's increasing. It's not like tapering off, it's actually going to be increasing. So if I plug in our favorite number, 0, 0, 0, plug in x equals 0, I see y equals 0. And then if I plug in 1, keep in mind that this type of questions is a no calculator for your quiz. So, I'm not expecting you to do 5 root 2 in your head. What I want you to do is know I have a point 0, 0, and it goes this way. That's what I want from you. Because if you put in f of 1, 5 root 2 times 1, 7 point something.
Yeah, it's a little bit over 7.
Yeah. So I just want it to be like this. I just want to see this thing right here. It doesn't have to be exact. The point I want exact, 0, 0. Your graph should not be straight. It should not be tapering off. Those are wrong. And ideally, you have enough sense that it's not going to be this wide, fat thing. Like, no, you know it's going up. Even if you had it like this, that would be fine. Because you're showing me it's only one part, only in one quadrant. And you're showing me it starts at 0, 0. That point has to be exact. The rest, it's skinny enough. I don't know who we left off on. Domain, let's start with Sarah and we'll go the other way. Sarah, what's the domain here?
The domain is greater than 1. Greater than 0.
Yeah, 0 to infinity. So we have a square bracket around 0 because we're including x equals 0. And what is the range, Rocky? Exactly. Perfect. Danny, you want to tell us the x and y intercepts? Yep, for both, because that's where it touches the x-axis, that's where it touches the y-axis. Ethan, end behavior. What's the left end behavior? Exactly, there's none. Jake, what's the right end behavior? Exactly. It goes to infinity, comma, does not exist. Andrew G, where are we continuous? Good. So go 0 to infinity, and then where are we increasing, Daniel?
0 to infinity.
Good. Where are we decreasing, Tal? Nowhere. Perfect. So that's a good place to stop. Yeah.